And today's session is really an advanced look at some data review, really highlighting the diagnostic graphs in ARM. And I'm actually going to turn it over to Peter, our statistician, for the presentation here. And I'll just hang out in the background for any questions that you might have. And I will stop sharing so that way Peter can share his screen. If it'll let me stop sharing. Here we go. And Peter, you are on mute.
All right. So you all can hear me, I hope.
I can hear you.
All right, Matt, that's good enough for me. And oh, this is going to be fun because my control bar is going to get in the way. So let's take a look at the topic I'm doing for today, diagnostics and transformations. And I like to take a historical view on some of these topics like this, where I go back to some of what was written in the 30s and 40s and the problems that practicing statisticians and agricultural scientists or biometricians were going through as they tried to understand how to use the tools that we take for granted every day. Oh, sorry. So we'll be using a couple, 3 classical references, and I've got links to them that are on JSTOR. Should be able to get most of them if you want them. So the first paper we're going to look at is by, I believe it's William Cochran in Biometrics, 1947, Some Consequences When the Assumptions of the Analysis of Variance Are Not Satisfied. And we see the link to the JSTOR PDF version of this file, and text I quote from the sources will be typeset in a sans serif font. So those aren't my own words, they're usually the words of the original authors. Now, when we work with diagnostics, we are basically determining if the assumptions of the analysis of variance are satisfied. That is the key purpose of diagnostics, is to tell us whether our data are normally distributed, among other things, and then maybe make some recommendations about what to do when the assumptions are not satisfied. So first of all, we need to review the purposes of the analysis of variance. And from Cochran's perspective, the purposes of the analysis of variance is to estimate treatment differences that are of interest. In ARM, we tend to talk about, we want mean separation letters. Okay, we want letters to show up on our means table. We want some idea of the accuracy of our estimates. And that includes estimates of standard error, our standard deviation. We don't use confidence limits very much in ARM. And the fiducial argument was something Fisher was developing about the time that these papers were written and have fallen by the wayside. And finally, we want to be able to perform tests of significance. Specifically in tests of significance, we want p-values. Usually, that's what's associated with the test of significance, is a particular way of statistical inference, without going too much in the minutia of the many different methods of statistical inference. So some of the properties that we want with the numbers that we get is that when we measure certain estimates of differences, we want an efficient estimate, that the variance between the estimated value and the true difference is as small as possible. When we talk about the idea of accuracy, we want to estimate a variance term, or sometimes take the square root to give us a standard deviation term. And we want that to be the same as the expected value of the variance. Now, to go into the meaning of that takes some mathematics. But the practical consequence of it is you'll see it when we calculate standard deviation. We usually use n-1 to calculate standard deviation instead of n, which is, and we take account in degrees of freedom. Those degrees of freedom give us an unbiased estimate of our variance. And our variance that we're going to be most concerned with in these, the type of analysis we do is the residual variance. We also want to be able to perform tests of significance, and we want our tests of significance to be valid. That is, if we say a p-value is 0.026, then the probability of getting a greater test statistic, say a larger F ratio or a larger t-value, is really going to be about 0.26. Okay. If we misestimate our variance terms, then our p-values are not going to be valid. I'm having a sip of my tea. And we want the test to be sensitive in that real differences are detected as often as possible. These desirable properties are met when the assumptions of the analysis of variance are met. Now, for part of this discussion, we're going to assume three types of effects. There's a treatment effect, there's an environmental effect, and there's an experimental error. For most of us, that means our treatment structure and our replicate structure or our blocking structure, and then our residual error. So we're going to be thinking in terms of analysis of variance of randomized complete block designs. Okay. Now, the four things that are assumed about the analysis of variance is that the treatment effects and the environmental effects are additive. And generally, if we randomize appropriately, we will see that this is going to be met, and it's met so often in agricultural trials that we tend to forget about it. Okay. Experimental errors must all be independent. This is a little harder to take for granted. We assume the plots are exchangeable. We assume that you can apply a treatment to any one plot in the field and it's not going to make any real difference. But there is a test to see that these errors are independent. The two that are probably most familiar with you is that experimental errors have a common variance and experimental errors should be normally distributed. Now, in ARM terms, the statistical test we use for this is Tukey's 1 degree of freedom test and Moran's I test, which we only see if we use the spatial option in the diagnostics dialogue. More commonly, you will probably be more familiar with the Levine's test for homogeneity or heterogeneity of variance, depending on how you want to phrase it, and then tests for skewness and kurtosis that the errors are normally distributed. So the first example that we'll look at is the effect of gross errors on the assumptions of the analysis of variance. And this comes from Cochrane. It's his first example, table 1. And what he points out here is that there is an obvious value that's wrong. Okay, these are ratios of dry weight to wet weight. We can't have a value greater than 1. So that is clearly a gross error. And when we notice these, we can mark them as damaged or otherwise exclude them from the analysis. So I think I need to escape out of my presentation and we'll go over to my ARM trials. And here I have an example from, this is the Cochrane 1947-1 trial. If you got the email that we sent out, you'll see the original data that Cochrane presented. We see a trial where the outlier is marked as IID, and we see where we use an alternate method of analysis called the analysis of ranks. Now, if we move my, there, hide that over in the chat. Yeah, and Matt just made a note that everybody should be sending out, we'll get copies of the files when we send out the recording as well. Oh, I'm doing some strange things here with my screen sharing. I forget that I'm sharing screen so you can see what's going on my computer. Now, if we look at the column diagnostics, we see that there is a kurtosis, and that the kurtosis cannot be corrected by any known transformations. So if we look at the IID graphs, oh, I don't want that one. I want it to actually be a 2 by 2. I have to remember to do that. So the presence of this outlier distorts one of the treatments. And it does affect the appearance of our box whisker plots, but not so much as to trigger Levine's test. It does give us a problem with Shapiro-Wilks on the assessment data, but not on the residuals. So I should point out, I'll come back to this at a later point, but we tend to prefer to do our diagnostic tests on the residuals, because that is the component of the analysis of variance that is used for our standard error or our standard deviation. We see the indication of an outlier in our spread location plot, but what triggers a statistical test of significance is this kurtosis, which leaves this outlier lying well beyond the normal bounds of our values. Now, we do have tests for outliers in the diagnostics, but they are adjusted for the number of comparisons. And in this case, we have a small number of comparisons. I will point out the column properties. If we use the box whisker, we will find the outliers as well. It uses a slightly different mechanism for finding outliers. Okay. So let's go back to our presentation. So I think this really just repeats what I talked about just now with the trial file itself. The kurtosis is not corrected by a transformation because it's not due to some underlying property of the data itself. Transformations tend to work best when the data are distributed in such a way as we don't expect normality, but we can transform to normality. So let's move on. Now, if we do the analysis with the data marked as IID, including that outlier, what we see is we have this efficiency of the estimate, I believe is the statistical property that we want to. And if we take out the outliers, we see there's quite a large difference between these two estimates. Column 2 excluded the outlier. And that the presence of that outlier takes away our ability to get a good estimate of the true value of the mean. All right. We also can ignore the true values of the means and only worry about the ranks of the means. And in that case, the outlier has a less disruptive effect. And in both cases, we see mean separation letters that are plausible and believable, although they don't get quite the same values. So the analysis of ranks is a tool we use when we can't correct for normality or we can't restore the data to the assumptions of normality. And it will typically be recommended when there are no known transformations that allow us to meet the assumptions of the normality. If we don't meet the assumptions of normality, the assumptions in analysis of variance, we tend to recommend the analysis of ranks, in which there are much less stringent assumptions about our distribution of our data. It's called a non-parametric method because we don't worry about finding a parameter for means and standard deviations. And ranks behave better than raw values. Okay, so let's move on. The effects of heterogeneity of errors is probably the one that's going to give us most problems when we try to use the analysis of variance. The nature of the analysis of variance is we take the individual standard deviations for each treatment and attempt to pool them into a common standard deviation. However, if the standard deviation varies a lot from treatment to treatment, and that's what we mean by heterogeneity, is that the treatment variances, the treatment standard deviations are not comparable or not combinable. Then we end up with the validity of our estimate of our errors and of our variances. So Cochrane's example, 1472, and we'll go ahead and pull that one up. Let's see, I've already gone through Cochrane 1, so we can close Cochrane 1. Hopefully it's not going to do my check for updates. Cochrane 2 trial. We are close to, but not statistically significant for the Levine's test. So we don't see the options of the other tests of the analysis of variance. I'm going to show up here. We don't see enough of a difference in our statistical test for the assumption of heterogeneity to reject the null hypothesis that there is no heterogeneity, although this is a bit worrisome. And we see it in the skew location plot. The skew location plot is going to give us a hint of what is causing the problem. And we see the spread among the residuals is much smaller for larger values and large for smaller values. And we also see it in the assessments. And that also introduces a skewness to our data, given the nature of the spread of the data. Now let's go back to my presentation. There is a feature that I'm working on, and I don't know which release it's going to be in, whether we'll have it finished up for the December release, that lets us decrease the significance of our tests for heterogeneity and homogeneity. And we see that we find that we cannot correct for Levine's error, Levine's homogeneity of variance test using the standard transformations AL and AS. The data are outside the range of an AA transformation. And since none of these really improve upon the heterogeneity, we might again have to ignore our assumptions of the analysis of variance and go with analysis of ranks. That's why I included in the example file data columns and we can use to compare the effects of the transformation. Again, this is one where we're really close to being problematic with our data. And it is a type of problem as again, to repeat what I showed, that is not easily corrected by a data transformation. And we see that issue in the skew location plot, where we see a wedge pointing to the right. Wedges pointing to the left are easily corrected with transformations. Wedges pointing to the right are not. And so if we have problematic data and we don't trust our assumptions of the analysis of variance, we would want to prefer an analysis of ranks. Just a brief note on the partition of error in randomized blocks. I decided to stick it here in the middle, that they considered tests of heterogeneity and homogeneity. And they found that the heterogeneity of error in Bartlett's test was reached at a much higher than 5%. At the 5% level is reached in 13% of the samples. There is a marked tendency to conclude that there is heterogeneity of error when in fact the normalized orthogonal comparison is subject to the same error variance. That's a way of saying that we can pool the standard deviations of each treatment to get a common error term. And the takeaway from this paper is that we use Levine's test on the residuals of our, we do our tests of normality on the residuals of the data, and that we use Levine's test for homogeneity in favor of Bartlett's. So this is a recommendation we've been making for some time. And I just wanted to throw in a slide to show a reference where we come up with that recommendation. So the next paper we run into, the next example from Cochrane, is the effects of correlation amongst the errors. And this is the example data. It is a kind of a small trial with only 2 replicates, and the blocking pattern where the effects are in blocks, and it makes a fairly a more uniform rectangle, suggests that we may improve upon this trial by using spatial models. So let's escape out of this. And we can close this one, I believe. Cochrane trial 2. And we see from these data under the normal conditions that there is no variation, or there's no violation of the assumption of analysis of the assumptions of the analysis of variance. Let's get rid of that. But part of our problem is that we're not going to have a good test of Levine's because we only have 2 replicates. And so our kurtosis is always still going to have a bit of a strangeness to us, because it's going to be a balance in the residuals when we account for the block effects. And the same thing with skewness. We're not going to get a good test of the assumptions of the analysis of variance because of the simple fact that this is in 2 replicates. What we might want to do, though, given the nature of the trial map, is to include spatial diagnostics. And in spatial diagnostics, we see 2 statistics. We see the Moran's I, which is a measure of spatial correlation. And in the original data there, in the data uncorrected for the block effect, there is a significant amount of spatial correlation. Moran's I is typically going to be a small, between -1 and 1, roughly. It's a strange calculation. And the preferred value is a slight negative value. Okay. We also have Tukey's 1 degree of freedom test when we use the spatial diagnostics. We're not going to worry about that now. What we'll do is we'll pop up diagnostic graphs, and we see Moran's I is telling us that this clustering in replicate 3 is having a significant impact on the lack of independence in our experimental units. Clustering is a way of saying that there is a dependency structure among our experimental units. Now, when we take the residuals, we improve upon Moran's I, but there is still a degree of clustering among our experimental units. And the semi-variogram, which is something we've recently added, shows the degree of correlation or similarity among adjacent experimental units, where we look at the plot-to-plot distance. And this is a measure of the variability or the variance among units. So it's kind of the inverse of a correlation plot. Plots that are close together are much more correlated than plots that are further apart. That's how we interpret the semi-variogram, and that complements Moran's I in a measure of correlation. This dependency structure is less when we account for the 2 blocks as separate effects. We would prefer, though, a quadratic spatial term, which greatly improves upon a Moran's I value. And we'll pop up that diagnostic. So here we go to a smaller Moran's I, and we see that there is less dependency or less correlation among the supposedly independent experimental units. It doesn't get rid of all of the correlation structure, but it does improve upon the assumption of independence among our experimental units. Now, I'm not going to go into a lot of details on Moran's I, but we will go to, under GDM statistics, resources, statistical verification. We have a web link called measures of spatial correlation. And we show an example of what a positive Moran's I looks like, where all of the large values tend to be on one half of the field, all of the small values tend to be on the other half of the field. Perfectly correlated would be basically 2 blocks of identical values. Okay. So we see that the values are segregated within the field, will give us a large Moran's I value. In contrast, a negative Moran's I value gives us something like a checkerboard pattern, where we alternate between small and large values. And here I show an approximation of a checkerboard pattern using values from the field trial itself. So that's a negative Moran's I tells us an anti-correlation among our structures. Okay, so let's see. And I include this an example to run the analysis. I don't think we're going to have time in today's presentation to go through all of the analysis. But that's what we look for when we look for Moran's I and our independence of experimental units in field trials is a correlation among the plots. Let's go back to the presentation. And I think I've covered this. There is a better example of Little, Millikan, Stroop, and Wolfinger, a SAS system for mixed models. This is a winter wheat yield trial. And it should be apparent from the trial map that this was not an appropriately blocked trial. And we see that these data in Little 1996 do fail most tests of normality. and we really don't have a good way to correct for it with a data transformation. And so the analysis of ranks is assigned. It looks like I'm going to want to go to escape out of here and go to my trial file. Oh, I don't have it open. I'll have to find it. Let's see, diagnostics. I want to go test cases and knowledge base. Textbook examples. So again, under the common transformations don't help our improve our normality of our data. But if we include spatial models, we do get recommendations for a cubic spatial trend model. So let's look at what a cubic spatial trend model will do for our analysis. And you see our Levine's test is going to suffer when we use a cubic spatial model. Although we do get improvement on our Shapiro's Wilk test, we do get improvement of our skewness, and we do get some improvement of our kurtosis. And we see that our Moran's I is going to be improved upon by our inclusion of a cubic spatial trend. Let's go back and show what the trial assessment map looks like in the residuals diagnostics plots. We see this quarter of the field here has a low yielding part, and then the lower right hat, or the roughly the right third of the field, is high yielding. And so our arrangement of blocks do not capture the spatial heterogeneity. One thing I should point out on this too is that our Tukey's 1 degree of freedom test shows that there is a suggestion that the blocks aren't additive, that we can't just take a measure of what the block mean is and include that in our spatial model the way we typically write it. Not quite so much to fail the test statistically, but it is of concern. So this is an example of where we have to be careful in how we lay out our blocks. And most of you who are using ARM are going to get blocking schemes that are not going to violate some of these assumptions. Okay. Although it is possible to execute a trial that doesn't capture the spatial heterogeneity, we can at least assume additivity of the replicates. I will point out that we also have in our column diagnostics, our resources webpage. I'm going to go see if there's anything. Nothing's popped up in the chat. Good. So I'm not losing anybody, I assume, since there's nothing in the chat asking me to move on. So when we talk about additivity, normally we would write our statistical model for a randomized complete block as a mean plus a treatment effect plus a replicate effect. We can't include the treatment by replicate interaction because that ends up absorbing all of the residual error. And so residual error and treatment by trial interaction are the same in RCB. We can, however, include a multiplicative term, and it is a test of this multiplicative term that Tukey is 1 degree of freedom test is attempting to determine if there is a slope associated with the treatment by the excuse me. And this is a lot of the mathematics that go into the calculation that we don't need to worry about today. I'm just pointing out that we have that information available on our website. So in a nutshell, if we don't randomize appropriately, we have a good chance of failing one or more of the assumptions of the analysis of variance. And when we fail the assumptions of the analysis of variance, we are going to get recommendations to use the analysis of ranks. And so I think we cover most of these already. So now we can move on to the use of transformations, which we'll try to touch in a little bit on the rationale of transformations and when they are best applied. Now, there's a lot of theoretical discussion that I've included in these slides. But the primary concern is that we choose data transformations. And again, I'll remember that these papers were being written when we were still trying to discover, the scientists who were working in the field were still trying to discover the mathematics that best apply to the situation. And there's still a lot of statistics that were being discovered. Let me go to play on this one. So the main thing that we look for in a transformation, that it is valid, that if we get a p-value from the transformation, that it is close to the true p-value. What we are going to find when we look at transformations is we look for transformations where the variance, we look for data where the variance is a function of the mean. And then we use that function to normalize the variance, to put it on a homogeneous scale. And I'm not going to go through this calculus. This is what Bartlett put in his paper, and finds that if we have the two that are most commonly used follow from this notation. Okay, here are also some notes about the desirable properties of transformations, and they relate back to the desirable properties for the analysis of variance. So we'll first start with a square root transformation, because this is the one where we can have the most mathematical justification for it. And the square root transformation is most commonly applied when the assessments that we are getting follow a Poisson distribution. And Poisson distribution are all positive integers. Zero, and I should say non-negative integers, because 0 is a possible value in a Poisson distribution. So Bartlett's example from 1947, I don't think I'm going to pull that one up because it turns out to be not the best example, in that we really don't need to transform these data. Okay. On a theoretical basis, so we don't, sorry, we do need to transform these data for Shapiro-Wilks because there's a lack of assumption of normality. But I don't know if Shapiro's Wilks test was that in common of practice at the time of this writing for this type of data. If you know you have count data, that's where the rating type or assessment, the basis drop list comes into play. Is there are certain types of data where we can tell from the distribution, from the type of data, what the expected distribution is, and make a more specific recommendation of the transformations available. So I guess I'll go through that real quickly. And we'll close little. We'll go to Bartlett 2. And so Bartlett 2, the transformation we make based on the assessment values is the autolog transformation. The autolog transformation is a general tool for data that don't follow a normal distribution. However, if we want to stick with the best theoretical transformation, then we're going to go with the arc sine square root, or the square root transformation. That unfortunately doesn't correct the data. So even though Bartlett used this as an example of data that could be transformed using the square root transformation, it isn't the best example we have now. So let's go back to the presentation. A better example is Bartlett 1936, some notes on the insecticide tests, which also has count data due to the number of insects. So let's go to that one. Let's see, it was 1936B. B2, let's make sure I grab the right one. 1936 V1. And so if we look at the column diagnostics, oh, sorry, I'm on the wrong one. The column diagnostics, and we do see the problem with the heterogeneity of variances. And if we use just the best transformation according to the one that gives us the most improvement of the Levine's test, then we are going to select the log transformation. If we use the theoretical basis, we get the arc sine square root transformation. So let's take a look at what's happening with these transformations. We show the transformation. What we want to look for, I don't use the box-Wister plots as much for detecting heterogeneity of variance. I find that the wedge shape in the skewness in the spread location plot is usually a better indication of whether there's a problem with heterogeneity of variances. And we see in the untransformed data a distinct wedge shape where there's smaller dispersion around the smaller values, and that the this wedge shape is corrected by the square root transformation. Let's see, I've got a couple chats here. Let's see if there's something quick. Okay, we've got that one. Thank you, Matt, for taking care of that. So again, the point is that this is the skewness location, the spread location plot is generally a good indicator of whether you're going to have success with the transformation or not. Now, let me go back to my slide. So this is one where these data should be transformed, and the square root transform is the theoretically best transformation. So again, unconstrained values recommends we use AL, the rating type selected AS. And a similar example is Bartlett 1936, where we're looking at insect counts, the square root transformation, the analysis of variance. And in the case of Bartlett 1936, number 2, table 2, we have two different recommendations. One is an AS transformation and one is an AA transformation. Sometimes when they're inconsistent, you might go to the rating type and you'll get a consistent recommendation for a transformation. When we do the unconstrained transformation, we look at just the test statistics and the transformation that most improve those test statistics. When you have a rating type that we know the family, we know what type of distribution it belongs to, and we know when it's a non-normal distribution, we can make better recommendations if you choose the rating type based on either the rating data type or the rating unit for the basis of a transformation. Now let's move to the logarithmic transformation. And there is some more notation from Bartlett 1947 in that sometimes the square root transformation doesn't stabilize the homogeneity of variance because it's proportional to the square of the mean or some other nonlinear value. Now, I didn't put this in there, but when we have count data, we have a Poisson distribution, and in the Poisson distribution, the mean and the variance are equal. There are no two different parameters. There's only one parameter. It's the mean. The variance of the Poisson data is also the same as the mean. So it works quite frequently well that to take the square root of the raw data converts it to a normal distribution. But in Bartlett's 1947 table number 3 example, there is considerable heterogeneity present, and it is still correlated with the data on the square root scale, and may only be stabilized on the logarithmic scale. Now, these are a couple graphs that I'm working on that I'm trying to decide if it's worth to include in column diagnostics, where we have the treatment mean and the treatment standard deviation. And we see that the treatment standard deviation is larger when the treatment mean is larger. If we take the arcsine square, the square root transformation, we see that the mean is the treatment standard deviation or the treatment variance is still proportional to the treatment mean. When we apply the log transformation, this actually overcorrects a little bit, where the treatment variance decreases with the treatment mean. So we're kind of caught in between two potential transformations here. Both tend to improve the assumptions of the analysis of variance in that the variances are homogeneous, heterogeneity and homogeneity, and now my words are getting all mixed up. But the autolog transformation goes a little bit too far. And so again, both AL and AS improve the heterogeneity. We don't include in this the AA transformation because it falls outside the limit of percentages. So the takeaway from this in that with working with transformations is when you are working with count data, the square root transformation is going to be the theoretically preferred transformation. However, in biological data, we tend to see more variability when we have larger values, regardless of what the values are derived from. And the log transformation is going to most commonly correct for those types of variances. Now, I want to only touch briefly on the arcsine square root transformation. So let's go back to the presentation. The arcsine square root transformation, and the reason I noted this in there, when you have proportions, it bears the same relationship in probabilities, proportions following a binomial distribution, where the variance is the probability or the proportion divided by the number of samples. It follows the same relationship to that type of distribution as the square root transformation does to a Poisson variant. So when we know we have proportion data and we choose the data rating type or the data rating unit as the basis for recommendations, we will more commonly get an AA transformation. One of the reasons that we have AA transformations are going to be preferred for proportion data is that they are going to be bounded above and below. And so the transformation, the variance has to have a kind of symmetric effect on the endpoints, where we reduce the variances the most in the middle and have little effect on the end. And so this case shows the difference between the transformation in skewness between the untransformed data for Bartlett's 1947 number 5 example and the transformed data using the AA transform. Let's see, I don't want to escape just yet. And again, this is a slide I'm working on to show help us decide our choice of transformation. And when the variance is proportional to the mean, we don't want to recommend an AS transformation. And in this case, AS or AL is not going to improve our homogeneity of variances. So those were the slides that I wanted to continue with today. I have a few extra slides that you can use. I'll try to run through them briefly real quick. Gomez 1984 Statistical Procedures for Research have some recommendations for the logarithmic transformation when the standard deviation is proportional to the mean, and have the Gomez 719 is a nice example of where we have data that are more spread as we get to larger values. And so this is a good case of a logarithmic transformation, although we still see a little bit of a wedge shape in the spread location plots. But this is something you will see in column diagnostics that will give you an indication where your data could be transformed and be improved upon with the transformation. And again, this is quoting from the text of Gomez and Gomez, where the square root transformation may also be useful for percentage data when there's a range of values. We don't include that recommendation in our diagnostics plot. I'm going to go back to play here because I don't think I'm going to go to the slides, the ARM files anytime soon. All right. So this is another recommendation for when to use transformations. Oh, why did I do that? And Gomez and Gomez have some further rules for transformation. If the data are in the range between 30 and 70%, we very rarely need transformations. If they are in 0 to 30, the square root transformation should be used. 70 to 100, we can use a square root transformation, but we usually take the 1 minus or 100 minus of the original value. ARM doesn't do that kind of transformation. And if the data are outside those ranges, then the arcsine covariate transformation should be used. So you'll have these slides available for your own references and to help you decide what transformations to apply as you go through and examine your data for the assumptions of normality. I also include quotes from Steele and Torrey. One reason we haven't encoded any particular range values for percentages is Steele and Torrey recommend 0 to 20% instead of 0 to 30% for the recommend ranges for arcsine square root or square root transformation. So there is a little bit of disagreement in the literature on the best range of values. And Steele 7.8 is another reference I included in here. I started developing the idea of the mean versus standard deviation plots. I found one in the Beale paper in 1947. This is a reference from analogical field experiments, so insect count data. And when transformations are necessary, Snedeker and Cochran is another reference for when transformations should be applied, and it's one I'm using to develop these ideas of plots of the standard deviation versus the mean. And Cochran and Everett is a nice reference that I found in log transformations, showing how the log transformation is useful when the spread location plot shows a heterogeneity of variance associated with the treatment mean or the predicted mean. And again, the relationship between those two. So that is the presentation for today, which brings us about to the end of the time. So let's see where we have any chats. And we do have, there are automated transformations in ARM. Will they search for the correct transformation? That is a problem. That's a difficult problem to answer. Historically, ARM, when you run print reports, and I don't know if I have one handy, does have, let's see. Matt, you're going to have to chime in and tell me which one is
the general summary.
General summary.
Second from the bottom.
Okay, apply automatic transformations prompt. There we go. So this is something that was developed quite some years ago, and it will go through, and as we analyze the data, we'll attempt a series of transformations. Some include excluding replicates or excluding treatments. This historically has been on the raw data itself. And I tend to prefer not using these in favor of the column diagnostics, where you actually look at here, and in this case, in the diagnostics dialogue, we will make recommendations for transformations only if the data fail the initial test of heterogeneity of variance. That is, if we have a significant p-value in the diagnostics for the Levine's test to Shapiro-Wilks, skewness, and kurtosis. And we want you to go through and individually check each data column using the column diagnostics tab in order to correct for data transformations. One of the reasons we want you to do that, and I think I did find a case where sometimes the recommended transformation does not improve upon the assumptions of the heterogeneity of variances. So let's see. Yeah, Matt gave the right short answer. We go to this example with little. And we'll just do column 1. Now, this one, let me just check to see. Nope, it didn't. In this case, we didn't fail any assumptions of we did fail. Why didn't I get a prompt, Matt? You're going to have to remind me of why that one didn't fail. So we do show in this case the possible transformations. And if we look at Levine's test isn't the problem. It's Shapiro's Wilks and the general test of normality. And Shapiro's Wilks is a general test of normality. None of the available transformations will correct the data. So there is no good simple recommendation. And that's where we get the analysis of ranks. But we also want you to explore whether a spatial transformation will improve upon the assumptions of normality. And so we give you these tools in the column diagnostics table, the column diagnostics dialogue, to actually look at whether the recommended transformations will improve upon your normality of the data, which is not something you get to see in the report options. Okay. Yes, it is. It'll be analyzed and a warning will be produced. You can do this automatically. Let's see. I lost track of which was one of my good examples of no, that's not the one. I think I may have closed that one already. So there will be cases. Oh, this is the one. Where you might get inconsistent recommendations for the best transformation for your data. In this case, the square root transformation best corrects the Shapiro's Wilks. So the Shapiro-Wilks is a general test of normality based on the QQ normal plot. And we expect our values in the QQ normal plot to fall within these 2 and 3 standard deviations of the mean. If they fall outside, there's a general problem of normality. And in the AOV, we still see some problems with the assumptions about the normality of our residuals. We also see that there's a kurtosis because of the shape of the residuals. Now, because we have that inconsistency, there is no single good automatic transformation to apply. And this is where we want you to go into and look at things like the rating unit or the rating type to find a more consistent recommendation for the transformations to be applied to your data. So that's another reason that we tend to prefer the to leave that as no. Let's see, let's go with prompt. So unfortunately, sometimes what we worry about is we do see that we do get the warning that data has skewness, and we get information about what to do. But unfortunately, I think a lot of time people will click through these recommendations. Just click OK, not even look, particularly if they're in a hurry. We want our users, our clients, to get in the practice of going through the data using the column diagnostics. And one thing I will note is that the pop-up recommendation is based on the raw values. And we now prefer to use the residuals. So the residuals from the, we use the notation IID to imply that is a code that will be transformed, put into the ARM action code, meaning that this column has been examined and is been decided either through column diagnostics by someone looking at it or someone who is manually typing in IID, that this data column has met the assumptions of analysis of variance. And we started out this presentation with some of the important things, the important assumptions of the analysis of variance and what it provides us with our data. Okay. So I guess that's my long-winded way of saying is that we want you to go through the column diagnostic dialogue. And we've made it fairly easy because we can just go next to step through a series of assessment columns and then click on in this diagnostic dialogue what should be applied. We can double click here in the recommendations and that should do it too. So we can make changes to our so we're past our allotted time for this presentation. Are there any further questions? And I don't see any in the pop-up.
Feel
So
free to send an email to us if you do think of one later. Thanks, everyone.
So I'm going to stop sharing my screen and turn the meeting back over to Matt. And thank you all for sticking with me.
Thanks, everybody.